Back in 2011, you may remember the earthquake in Japan. Um, we kind of, think about the reactor, the nuclear reactor that had issues there where the radioactive materials were sent into, the open. And so in this clip that I show in class, it shows some folks in the high-rise buildings in that city, and what ended up happening is those buildings were actually shifting back and forth. And as they were shifting back and forth, it was pretty slow. I mean, but these actual buildings, this would be a little bit exaggerated, but they actually shifted back and forth. And so, trying to draw that here. And as they did, right, it was forced back this way, then it was forced back this way, and it went through the middle. And it did it for a considerable period of time. And what's important with construction is that you don't build things too rigid. If you build things too rigid, and you have some forces on it, instead of bending like this, they'll actually break, and that can be really bad. And so when we deal with objects that are moving like that back and forth, we call that simple harmonic motion. And this is going to be directly connected to wave motion as we continue here. So in simple harmonic motion, we have to assume that like for instance with this building, when this building is shifting, and shifting back and forth, obviously this is exaggerated, but when that building's actually in the middle, like where it's supposed to be, right? So this building's going back and forth, when it's in the middle here, it's neither stretched nor compressed. Similar to, if we had a example we like to use is a spring, and the spring has a mass on it, and this mass is going back and forth. As it goes back and forth, when it's in the middle, where it's, the spring is not stretched or compressed, there's no force on it. And so it's at the equilibrium position. And so the further it is from the middle, the more force that there is. And so, the further this building is from equilibrium, the more force it's trying to bring it back. And then when it's on this side, it's trying to bring it back this way. But when it's in the middle, there's no force on it. The way that we calculate how much force is on an object due to, the strength of the spring. So K is the spring constant in newtons per meter, the spring constant. And that's how many newtons it takes to stretch it a full meter. X is the displacement from equilibrium. And then F is the spring force, how much spring force that you have. And so we know that with that negative sign, it's the restoring force. In other words, if we had let's say we had a vertical spring, right? And let's say we stretched it, it's stretched now, it wants to go back up. So the force is this way, right? So we pulled it down this way, but the force is this way. So they're in opposite directions to each other. That's why we have the minus sign. And so as this mass, this mass can go up and down, up and down. When it's all the way up like this, right? It's, the spring is compressed. It's trying to bring it back this way. But the force is not constant because, when it's fully compressed, like if this spring is way, 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 way up here and the spring is all compressed, that's more force than if it's just kind of halfway. If it's halfway, the spring is not as compressed as much. It's not going to, apply as much force making it go down. So when we look at a, object, in this case here, that has a mass on it and it's stretched a certain amount from equilibrium, we have the force gravity on it, we have the spring force on it, we can figure out, the K value of it and that kind of thing. And so, depending if it's moving up or down or if it's just resting there, if it's just resting here, right, these two forces are equal to each other, and, we can figure out the strength of the spring in that case. So with Hooke's law, right, we have the force of gravity pulling it down, we have the spring force holding it up, and therefore we know that the weight of it is balanced out by the spring force. So to review, let's go ahead and try this here. We have, this is I1. What is the K value for a spring that's displaced 3 meters when a 50-gram mass is placed on it. So if we draw our mass and it stretches down 3 centimeters, which is 0.03 meters, stretched down like this, we can draw the free body diagram. We have the force of gravity, right? We have the spring force. So if we set up our sum of the forces in the y equals ma in the y, we have a positive spring force plus the negative force of gravity equals 0, right? So they're equal to each other. And yeah, we can calculate, the spring force. So go ahead and pause the clip. Go ahead and calculate the spring force, and then you can hit play when you're ready to check. All right, so you should get 0.49 is the force, and for the spring constant, 16.33 Newton meters. And so that's the strength of the spring. So in other words, if you had a spring, right, at the same spring, and you had this mass, and it was able to stretch for a full meter, it's going to take 16 newtons to do that, to pull it all the way down a full meter. If you notice in this case, this mass pulling it down only 0.03 meters, it's not as much force, only 0.49 meters. But if you stretch this an entire meter, it'd be this much force. And that's what K is. That's the K value. How many newtons for every meter that you stretch something do you have? So in this this link, I would encourage you to copy this link. Sometimes the permissions with Java is kind of tricky, but this is a great simulation to be able to see the motion of a mass as it goes up and down. And so yeah, if you want to try that, that would be great. This is another fun one where this is if you look up Veritasium and then look up bungee, you'll see the clip about this, and it's pretty neat because it applies what we're doing as well. So in terms of this motion, right, this object is, in this case here, is going back and forth. And so, if I were to draw this mass, the motion of it, right, it's going out here, and then it's coming back, and then it's coming out here again, and then back. And it's a periodic motion. It's going back and forth, back and forth, back and forth. And if the surface is frictionless, and then this spring isn't taking away some of the thermal energy, it's going to keep going on forever. But in real life, you have both of those, right? So it's oscillating back and forth. Each cycle takes the same amount of time, and this motion is called periodic motion. Periodic motion is where each cycle takes the same amount of time. So in other words, as this mass comes out to here, and then comes back over here, and then comes back to the middle, if we took that amount of time, the next time it goes around, right, like this, it's going to take the same amount of time. And so a full cycle is a period. So it has to go all the way there, all the way back. And this mass spring system is helpful visual for that. The building, like we talked about there, right, those buildings in Japan that were stationary, when they were moved, they were shooken, right? They're moving back and forth in simple harmonic motion. Take the same amount of time for that building to go all the way there, all the way back as it moves. So when we look at both force and energy, it's important to look at both. All right, so let's visualize the energy with this. Let's say we have a mass on a surface, and this mass goes out, is going back and forth. Let's say it comes all the way out here, and then comes back here, and then swings around, right? When this mass is way, way out here, and it's not going this way anymore, but it hasn't started coming back this way yet, the velocity is 0 at that spot. So because velocity is 0, we know kinetic energy of this mass is 1/2 mv squared, right? So the kinetic energy is 0. But if you think about it, right, this mass being way, way out here, let's just draw that, right? It is a certain x from equilibrium, right? If this is 0 here, it's a certain displacement. So we know the spring kinetic energy, or spring potential energy, P of a spring, is 1/2 kx squared, where x represents the distance from equilibrium, k is the spring constant. And so it turns out at the very, very end here, the potential energy is actually a maximum. It has a maximum amount of spring potential energy. And, likewise, where this mass comes all the way over here, way, way out here in the middle, or, so the spring is compressed. it's a certain x from the middle, right? And if these are usually the same length, right, as if it's in simple harmonic motion. So in this case, we also have a maximum of spring potential energy, 1/2 kx squared. Now in the middle, we actually have a maximum velocity, and if we have a maximum velocity, we have a maximum kinetic energy there. Now in between though, like right here, in between there, it's stretched a little bit, right? And it's also moving, so it has both, in between. So it's important to consider all of these parts. In the middle, again, all kinetic energy, no potential energy. At the compressed area here, all potential energy, no kinetic energy. And then at the end here, all potential energy, no kinetic energy. But in between, you have both. And we'll be looking at all sorts of different situations with that. Likewise with the building, right? This building, as it stretches, the engineers would have to know if the building's over here, if it's over here, or if it's in the middle, right? In the middle, it's all kinetic energy, but at the very end here, you have a certain amount of certain distance that it's stretched out, and so the engineers would need to know about that. So when we consider F equals ma, force equals mass times acceleration, we know that the force of a spring equals negative kx. The acceleration is directly proportional to how far it goes, right? So in other words, if you have a spring on a surface here, the further this is stretched from equilibrium, right? The further x is, the greater x is, the more force there is trying to bring it back, right? So the more force there is, the more acceleration we have. And this is a common misconception because the velocity over here is 0, right? So the velocity is 0 over here, but the force is a maximum. And because the force is a maximum here, we actually have maximum acceleration. So when the velocity is 0, we actually have maximum acceleration. Remember, acceleration is a change in velocity over time, right? So it's easy to get these two mixed up, acceleration and velocity. When this is way stretched out here, maximum amount of force, it's trying to bring it back. So it's not moving this way anymore, right? But it hasn't started moving this way yet. And so it's important to, think through that.